Okay, so our second talk today will be given by Maciej Dunajski from Kerr. We'll talk about quasi-local mass, Kerr horizon, and causality.
Thank you, Bernardo. It's a pleasure to talk at the Twistor program. This is, it'll be about mass, and I was, in some sense, won't be that far off from Blas's talk, especially in the second part. It's, so the problem with mass in relativity is an old one, whereas you might think that you can define mass of a region of space-time the way you define charge in electromagnetism by integrating charge density over this region. This is not something you can do because due to diffeomorphism invariant, there is no concept of local energy density. There are nevertheless ways to associate and compute mass at various infinities. So there is the ADM mass at the space-like infinity, or where I come from, we call it the Trautmann-Bondi mass at the null infinities, and they are known to be to satisfy positivity criteria. So and then there's a concept of quasi or program of quasi-local mass, which might well be a compromise between having these masses at infinity and having an energy density for a quasi-local mass. You would like to associate a number to a closed space-like two surface in space-time, and this two surface might be enclosing some region. So if you're, and this is a program which, as I understand, also goes back to Roger Penrose, the laws of possibilities, what this quasi-local mass could be and what you would want it to satisfy, and you would want it, for example, to be positive. But this positivity and some other properties you can list do not seem to lead to a unique notion of a quasi-local mass, and the laws of possibilities, and some are good for one class of space-times, other good for others. I'll comment a bit about these most recent possibilities, but the consensus is that there isn't at the moment a notion of quasi-local mass which serves it all. Right, so this talk will be two parts. I first talk about the quasi-local mass of a Kerr black hole horizons, and this, this will be done using a kind of isometric embeddings, and this is a work I did a while ago now with Paul Todd. And in the second part, I'll move away from quasi-local mass, but use another idea of Roger Penrose and talk about a global approach to mass, which is based on causality. And this is work I did with Peter Cameron, and also it's based on work Peter did himself more recently. Okay, so first this quasi-local mass, and this is just one of many approaches. It's in the family of what's called the Hamiltonian approaches, and it was initiated by Brauch and York, but the formulation I'll be using goes back to Kijowski and more prominently to Liu and Yao. And the idea here is as follows. So you have a closed surface with non-negative Gaussian curvature in a Lorentzian. This surface has non-negative Gaussian curvature. There are theorems, Weil and others, that there exists a global isometric embedding of such a surface in R3. Okay? So what you do then is you define, so this R3 will serve us as a reference frame, reference space. What you do is you declare this quasi-local energy, KLY, for me stands for Kijowski, Lau, Liu and Yao, to be an integral of a difference between the mean curvature of this embedding in R3 and a mean curvature vector of the way this surface is embedded in the four-dimensional space-time. So, you know, this is a vector and the norm taken with respect to the space-time metric. So you know, you have a surface sigma, which you'll view in two ways. First of all, it is a space-like surface in space-time. So you can, so by construction, it has been embedded in a space-time, and it has a mean curvature vector and the norm. But you're also embedding it in R3, and you take a difference of these two and you integrate. So this, those of you who know this Brauch-York definition, it differs from this definition in a sense that it's covariant. So in Brown-York definition, one would take a difference between the mean curvature of this surface in R3 and the mean curvature of this surface in some space-like hypersurface in spacetime. But that depends on this space-like hypersurface in the way that this doesn't. Okay, so what, you know, what about this formula? So in one sense, it's great because it's very concrete. I mean, if you like calculating, you can, you know, as long as you can find your embedding, you can sit down and you can calculate with it because there is a formula. And there is also a positivity argument due to Liu and Yao, which is based on another positivity argument by Shi and Tan. But the con is that, you know, shown by Murkada, Laszlo Szabadas, and Poor thought that this mass is in a sense too positive. So what they did is they found, you know, classes of closed surfaces in Minkowski space, and these surfaces have a property that they don't lie in a space-like surface where this mass is positive, but it should really be zero because these are surfaces in Minkowski space. Another disadvantage of this definition is that it's only applicable to surfaces where which have everywhere non-negative Gaussian curvature, because that guarantees this embedding in R3. So it for example, excludes the extreme or near extreme spatial cross-section of the Kerr horizon. So I'm going in this part of the talk, I'm going to address, tell you how to get around this problem, and then I'll come back to this too positive problem later. Okay. Well, there is, okay, so there is subject to some genericity condition, this embeddings are rigid up to a rotation. So for the surfaces we will be interested in, these are rigid.
So there is a mass.
That's right. But it's, you know, if you like, the constructing the isometric embedding is the fun of it, right? Well, you see. So let's talk about Kerr horizon, and I'll I write it in convenient coordinates. If you in the Boyer-Linguist coordinates and you focus on the outer horizon, replace what would be called theta in the Boyer-Linguist coordinate by its arc cosine, which is x. You'll find that the metric on the spatial cross-section looks like that. So here, okay, so lots of parameters. There is m and there is a j. But it's convenient. So out of m and j, you construct this constant rho, and that pre-multiplies this metric. It looks like a metric with a U1 isometry, which it is. It's also convenient to construct this constant c, which goes between 0 and 1, and the coordinate x, because it's cosine, goes between -1 and 1. Okay, so our task will be to try to, so we'll be computing the quasi-local mass of this. So we need to embed it first. So you compute, it's very explicit, you compute the Gaussian curvature, and you find that this Gaussian curvature is bounded from below, as it should be, because this is, the underlying surface is a topological two-sphere. But depending on this range of, depending on the value of this constant C, which itself depends on the value of ratio of J to M, this Gaussian curvature can be bounded by something which is actually negative. And if C is large enough, which in the Kerr language means if the angular momentum is large enough, you'll find that there'll be regions. It won't be negative on the whole of the surface, but there'll be region near the poles, north and south pole on the sphere, such that this minimal Gaussian curvature is negative, only for certain value, certain range of the angular momentum. So you expect to have problems with, the fact that Gaussian curvature is negative doesn't yet mean that you cannot isometrically embed it, but in this case, it will mean that you can't. So what this Weil-Nirenberg theorem tells you is that if Gaussian curvature is positive, then you can definitely embed it. But here you'll fail. Okay, so what's the idea? Well, in the range of C, where the Gaussian curvature is non-negative, we can actually find the global embedding in R3, which also preserves this isometry, and compute the mass using the standard formula. In the range where the angular momentum is large, so close to extremal Kerr, we don't, it turns out, have an isometric embedding in R3, but there is an embedding, in fact, the whole class of embeddings in the hyperbolic space. And I'll tell you how the curvature of this hyperbolic space will be related to this minimal Gaussian curvature. So we're going to use two different embeddings in these two different ranges in a way that they'll be, this kind of, as a function of C, the resulting mass will be continuous at C equals 1 over √3. It's a can. It's a can. Well, okay. So I'll bring up a theorem which will tell you what the curvature is. So the deal will be, if you tell me what's the minimal Gaussian curvature, which is some negative number, I'll tell you what is the least curved hyperbolic space in which I can embed it in. I don't know, but I'll come back to some interesting values of J in a moment. This critical, I don't know which one. Perhaps not, and perhaps it's just an formalism artifact. Okay, so let's first look at the case where you can embed this in R3. So I'll call them slow rotating horizons. Well, how do you go to construct this embedding? Well, you write your R3 metric using cylindrical coordinates, and you find by explicit calculation that setting zeta to be this function of x will do the job. Okay, and then you can, for this embedding, you can calculate the Gaussian curvature and the mean curvature. So the mean curvature is plotted with the red, and the Gaussian curvature is plotted with the blue. And that's what happens for some, well, relatively small value of what I call little j, which is j over m squared. So this little j ranges between 0 and 1. And this is what happens where little j is square root of 3 over 2, which if you repack it and you recalculate it using C, that corresponds to C equals 1 over √3. So this is this critical value of C, the last one where the isometric embedding exists. Okay, so in this range, we calculate the mean curvature of the embedding. And so I want to think of this quasi-local mass as a function of both m and j, although normally, for a fixed space-time, your j would be peaks, but that's, you know, the expression you get is not an elementary function, but you can expand it in a series, and that's what you get. And already at this stage, you've learned something new. So there is some old work on this quasi-local mass in this slow rotating regime by Martinez, who's conjectured that, who did this calculation to first order and conjectured that this quasi-local mass is always equal to m times 2 minus a quarter of j squared. This bit alone is called the irreducible mass Kerr. But we, you know, you see that even for small j, you'll have you'll have some corrections. So this quasi-local mass is smaller than that. Okay? But now we kind of entered a less familiar territory. So we'll really move away from the standard definition of this Liu-Yau mass. And that builds on this theorem, which I think goes back to Pogorelov, shows you this, that if you have a Gaussian, well, you have a surface with Gaussian curvature bounded from below by minus L squared, then you can embed it in a hyperbolic space, isometrically, globally, with Ricci scalar less or equal to -6 over L to the -2. So there is not one hyperbolic space, but a whole range where you can vary. You can vary its Ricci scalar, but we're going to pick reasons for it. We're going to pick in our embeddings the least curved hyperbolic space. Okay, and there's been some work on this isometric, hyperbolic isometric embeddings, not in the context of mass. They were interested in intrinsic properties, and this is by Gary, Cordero, and Rebello. So they've computed what the isometric embedding is. So you know, by an isometric embedding is you find, you can either choose to look for R as a function of X or Z as a function of X. They're looking for Z as a function of X. And we've added to this a computation of not only the Gaussian curvature, but the mean curvature, which you can again compute and then start plotting. And you'll find that in the whole range of C or J between √3/2 and 1, the Gaussian curvature can be negative and is negative next to this x equals -1 and 1. So they would correspond to the poles of the sphere, but the mean curvature is actually always non-negative. Okay, so now you compute this quasi-local energy as a function of this dimensionless spin parameter j over m squared. It's quite intimidating, but not too complicated, at least not for Maple formula, and that depends on C. And remember, C really is this little j. So you have this, and you have to integrate that, and then you find something which, though we thought and probably still think is strange. So you first have, so this is now, you know, we patch this isometric embeddings in R3 and the hyperbolic embeddings. And we find that the mass in the Schwarzschild case, that's j equals 0, the mass is twice the ADM mass, okay? And then it's decreasing as a function of j to some value which is around 1.79 of ADM mass. There you use hyperbolic embedding where it's increasing, and it looks like a straight line, but it isn't really. But if you look very closely here, or less closely there, you see that it actually doesn't peak at j equals 1, but it peaks just before that. So this is a maximum. And we've asked people here and elsewhere, people who really understand what it is to do numerical integration, because this integral has to be done numerically, so how to make sure that this maximum is not an artifact of our numerics, but it was explained to us that it isn't. We're very grateful to these people. So the conclusion of this is that this E attains a maximum at this large value of j. So I have no explanation of whether this is a physically interesting value or not, except that to say, well, but it's close to 1, right? Close to 1, and there is evidence that other things, interesting things, happen for J close to 1. So, for example, there is an old observation of Kip Thorne is that if you want to understand Kerr black holes, which are in equilibrium and they absorb matter and radiation from accretion disk, then J has to be this, right? Which is not quite what we have, but also close to 1. There is a more recent, well, back then it was a preprint, might now well be a paper by Don Page, who considers what's called Kerr boomerang. So there is he looks like a Kerr photon sphere, an analgeodesic emerging from the axis near the North Pole and re-emerging through the axis near the South Pole. And which I forgot the details, but there is a nice calculation of Don's. And this boomerang effect happens for this value of J, which is, well, again, not ours, but also close to 1. J equals 1 is extreme, and we can thought that for extreme this mass will peak, but it peaks before that. Okay, so that's right. So okay, so this is the end of the first part of my talk, quasi-local mass, and we kind of, the reason I'm talking about it now, having done this work 3 years ago, 2 years ago, 3 years ago, we're looking at this again in a different context with my student Alex Cooling. So for example, there is an observation. So it's interesting to do this in a cosmological context. It turns out that if you have both lambda and m, and you look at the extreme Kerr, the Sitter horizon, then you can embed it. Although it's extreme, you can embed it in R3 for certain range of mass and lambda, and you can also embed it in H3, and you can compute this mass and kind of thinking which embedding is better and why, but that's work in progress. Another connection we're hoping to make is with what is now regarded by experts, of which I'm not one, as the best definition of quasi-local mass. So this goes under the name of Wang Yao mass. See, the point of this paper was to address 2 problems with Liu Yao mass at once. So one of these problems is that it's only applicable to surfaces embeddable in R3, so with positive Gaussian curvature. So we gave you a way to overcome this problem by hyperbolic embeddings, but I'll do something else. Another problem is this positivity or over positivity issue, and they really solved these both problems at once by instead of using embeddings in R3, they use embeddings in R31. So there is embeddings in Minkowski space as a reference frame. And I'll give you a bit of details in a moment, but the way this solves this over positivity observed by Paul and collaborator is it attributes this to a momentum. So what you should really be looking at is not quite mass, but the energy momentum tensor. Now, what is this emergence of R31? You see, that's at the level of embeddings is quite simple and neat. So let's say that you're given a sigma, and sigma has a metric which has in some regions negative Gaussian curvature. So you might not be able to embed it in R3. Well, what you can do is you can seek a function, let's call it tau, such that G plus D tau squared, so this is a new metric on sigma, that this has positive Gaussian curvature. Well, this you can embed in R3 for some tau. But you see, if you've embedded, but you haven't really embedded the metric you wanted in R3 because you've embedded G plus D tau squared. So what you then do is you subtract D tau squared from both sides of your embedding formula, and you've convinced yourself that you've embedded your surface in Minkowski space, R31, where tau is some graph of a function. But now, by doing that, you've introduced this tau, and how do you know which tau is better than other taus? Well, you have to, that's where it gets complicated. So there is, you can compute this mass then with respect to any embedding and any tau, and you find an infinity of this mass over all possible taus, which is a variational problem for tau leading to some equation. And that makes, in my mind, that makes this somewhat less constructive, because it's not just that you have to find an embedding. In some sense, you have to find all embeddings and pick the best one. Again?
You don't get it.
You do. I think it's called the Young equation. It's a complicated variational equation for tau. Okay. Wait, I'm going to rubbish string theory on my next slide. So just give me time, right? But good thing for us, this in Paul, is that that even this nice embedding is not applicable if the mean curvature of the surface in space-time vanishes. Okay? For example, on the Kerr horizon. So we still thought there is a merit in us computing this mass of the Kerr horizon, extreme Kerr horizon, because the Wang-Yao definition wouldn't do it, except there are some approaches to do it. So there is one by Rai, Wang, and Yao, Miller, where they do it away from the horizon and try to take a limit. It's a bit shaky the way they take a limit, because the limit is complex, but they get some nice, I had correspondence with Wang about it, they get some nice answers out of this, which this monotonicity, except the peak agrees with what we do. And there is a more recent work by Zhao, Lars, and Yao. But I think you still encounter this problem, but the mean curvature cannot be zero. But there are attempts to generalize this to cases where mean curvature can be null, or a mean curvature vector can be null, or maybe time vector. So there is a work to be done, a work in progress. Okay, that's my second talk. And I'll talk about mass in a very different setup. So this will, unlike any other. So this is goes back to an observation I'll tell you more about in a moment of Roger Penrose, is that positivity or negativity or vanishing of mass affects asymptotic properties of space-time near space-like infinity. So there is, in GR, sort of, standard thing of the Shapiro effect, which tells you what happens to null geodesic near a massive source. So there is certain delay phenomenon. So this, the method or approach I'm going to tell you about is based on what might be called an anti-Shapiro effect, where geodesics, the mass has in fact of advancing null geodesics close to the space like infinity in the presence of mass, not otherwise. And this connection with mass is the subject of this paper of Penrose, Sorkin, Woolgar, which has never been published, but it's been very, very influential, certainly for us. Okay, so let me start off with something kind of solid and not quite directly related to the mass. So this is something Peter and I started calling the Penrose property, and it goes back to a not readily accessible paper of Roger Penrose from 1980 on Schwarzschild causality, a problem for Lorentz covariant general relativity. So in his talk, Lars said that the sort of instability of this extra dimension was part of Roger's campaign against string theory. This is an earlier part of this campaign, which predates that one by over 20 years. And you'll see why is it, why is this a problem for perturbation theory? Yeah, well, So what is this Penrose property? So there are two ways to formulate it. The kind of one which is finite, that doesn't use scry, and then one which is maybe conformal. So one definition is that asymptotically flat space-time admits a Penrose property if for any pair of endless time-like curves, you can find a time-like curve which connects them. So I'm saying that there should exist a point on one curve and another point on the other curve, such that you can construct a time-like curve between the two. Okay? There is an equivalent formulation of this property, which says that the property holds if and only if the time-like future of any point on scry minus contains the whole of scry plus. You can rephrase the last thing in the following way. So you pick a point on scry minus. So if you draw a Penrose diagram, this point is not just a point on the scry line, but it's also a direction. Any point is really a two-sphere. So to pick a point on scry minus, you pick a point together with a value of v, if you like, together with a point on the sphere. And then you pick another point on scry plus. So you pick a value of u and another point on the sphere. And is there a time-like curve connecting these 2 points? If there is, you say that the space-time has a Penrose property. If there isn't, you say that it doesn't. Now, so simple observation of Penrose is that in Minkowski space, in any dimensions, this property does not hold. So why doesn't it hold? Well, take Minkowski metric written down in these coordinates and take this two-sheeted hyperboloid. So you set all the coordinates from x2 to xn to 0, and then you take this two branches of hyperbole on the x1t plane. Okay, so whether you look at the finite or infinite or the conformal version of Penrose property, you can see that it doesn't hold. Maybe easier to see in the finite context. You have, I mean, there is no time-like curve connecting a point on the black curve to another point on that black curve. You would have to go outside the light cone. However, Penrose shows that in dimension 3+1, for the Schwarzschild space-time, the Penrose property does. Now, and that what Lionel says, why is this a problem for perturbative quantum gravity? Well, in perturbative quantum gravity or perturbation theory, you take metric and you expand it in some series with respect to the background Minkowski metric. Now, you would want, if you have two points which are space-like, by space-like separated, they're not connected by a causal curve, you would want the corresponding operators to commute. But if these operators, so let's see that you've done it to Schwarzschild. If the two operators commute in the Minkowski sense, so if the points are space-like separated by the Minkowski metric, then by this effect of perturbation theory, they'll definitely commute in the Schwarzschild sense. But this reasoning tells you that this is just wrong, because the Schwarzschild light cones are in a sense broader than the Minkowski light cones. So you can have points in Schwarzschild which are causally related, but they wouldn't be on the same space-time close to the space like infinity. They wouldn't be related by Minkowski metric. But this kind of interesting and I think still valid motivation aside, let's press on. So we have a theorem of Peter which tells you that this property also holds in Kerr. And so what's the argument for, since both Schwarzschild and Kerr? So this is what is the Penrose argument for Schwarzschild? Well, we'll be starting on scry minus. We pick a point, and this point, I should say, coming back to this Minkowski. Yeah, maybe I should have said it really. what really is going on here? It's not that you cannot connect any points on scri plus and scri minus in Minkowski space. You cannot connect the points which are antipodal on the sphere. So you have this sphere corresponding to a point on scri minus and a sphere corresponding to a point on scri plus. Most points you can connect, but the north pole on the past sphere and the south pole on the future one, you cannot. Okay, but yeah. I don't, but is Peter? Well, Peter is not here. So Peter Cameron has a paper about both ADS and DS, where the scries are not null, of space-like. But there is a version of this property, but I don't think I'm qualified to comment because both my memory fails me and I didn't do the work. But something happens especially in DS. I'm not sure about ADS. The analogous property holds, and I think in which one is it? It must be there is something which is called the Gao-Wald theorem. So this Gao-Wald theorem is applicable in DS, and it links with this property. I mean, it holds if you phrase it in properly. Right? So, but what happens in Schwarzschild is you start with a point on scri minus, so you're going to pick a V, and you're also going to pick some phi, an angle on the sphere, and you want to reach a U, and you want to reach any other angle on that sphere. So so your the question is, will you find a time-like curve along which this angle increases sufficiently, so it with a range greater than pi? And Penrose does it by constructing lots of geodesics and joining them from the segments. So there are these radial geodesics which don't change the values of phi, but there is a bit of non-radial geodesic until where the phi grows, but you have to reach it at the right place, having readjusted other parameters, and then you have to argue by estimates that phi will grow sufficiently large. And then what you do, so these are all null geodesics, but then what you do is you smooth the corners, so to say, and by doing so you make them time-like. Like a technical part for Kerr is that you use some sort of compactification of Kerr, and you enclose the Kerr light cones from below by something which is of course quasi-Schwarzschild metric. So you sort of prove Kerr by comparison with Schwarzschild. You say that the Kerr light cones are outside certain other light cones for which the property holds. Now it's interesting. So okay, so that's sort of another connection with Lars's talk. So as I understood it, and I might have misunderstood it, the original Penrose argument would have been about M4 cross Calabi-Yau, and you cannot quite show that this argument is wrong, but you're saying that if you replace M4 by M10 or higher, then there might be a gap in Penrose's argument. So it's not to say that there is no gap if dimension is 4, but there's something special about it. So here I want to finish off by demonstrating that there is something special in this Penrose property about dimensionality. So essentially, it's dimension dependent, even in the presence of positive ADS mass. So we can start off with 2 + 1 dimensions. So what is in 2 + 1 dimensions? There are no functional propagating degrees of freedom, but the way you think of mass, and that observation is due to a Polish physicist Staroszkiewicz, is that you can incorporate mass in the deficit angle. So you can write down this 2 + 1 dimensional Minkowski metric, where the range of phi is not between 0 and 2 pi, but it's greater or it's smaller. So you have an excess angle or deficit angle, And there is a way of relating mass to size of deficit angle. Right? And then you have 3 + 1 dimensional Schwarzschild metric, and you have higher dimensional Schwarzschild, where you replace what would be 1 over 2m, 2m over r to make v a harmonic function. You replace it by dimension-dependent harmonic functions. And you're going to ask a question whether this Penrose property, again, being able to connect points on scri minus and scri plus with causal curve, holds whenever mass is positive. And what happens if mass is negative? And so this theorem summarizes it. And the outcome is this, that if m is in Schwarzschild, if what we call m is greater than 0, then the Penrose property holds in dimension 3, 2 + 1 that is, and 4, and it doesn't hold if m is 0 or is negative. But curiously, in dimension 5 and higher, and that has to do with some decay rate, it never holds. So if you look at this metric with positive ADM mass, there is some sort of advanced geodesic effect, but it's not strong enough for you to be able to connect all the points. So that's, shows that, well, if you disregard number 3, it shows that this argument of Roger is unique to dimension 4. Okay, now moving away from the Penrose property, what does it have to do, or how does it relate to the positivity of mass for other spacetimes? So this is this argument of Penrose, Woolgar, and Sorkin with some expansion by Peter Cameron. So the underlying assumption is that every endless null geodesics contains conjugate points, and there are additional assumptions about asymptotic follow. See, what the argument is to show that if the ADM mass was negative, then the spacetime would admit something which they call the fastest causal curve. Then there is an argument that this faster causal curve, if it exists, is null. It's called null line, and doesn't have conjugate points, but you've contradicted your assumptions. Therefore, the mass had to be positive at the first place. And the idea of a fastest causal curve is that you pick a point on. It's not. You might think the way I haven't explained it yet, but the way I'm drawing it, and I'll attempt to explain it, you might think that it's equivalent to this Penrose property, but in fact it isn't, because this holds in higher dimension in the way Penrose property doesn't. So you pick a point on scri minus, and you pick another point on scri plus, and you compute what they call the time of travel between these points, and then you're trying to modify the curve to make this time of travel smaller. And if this sequence has a bound, you call the resulting curve fastest. And so it can either exist or it can't. And they show that if it exists, then the mass had to be negative. So this fastest causal curve argument was first put forward by Penrose, Sorkin, and Woolgar in 3 + 1 dimensions, where Penrose property also holds, and they capitalize on it. And then Hrustil and Galloway, and with fewer assumptions, Peter Cameron, proved that it also is valid. This positivity argument valid is in D + 1 dimensions. So if ADM mass is negative, then the fastest causal curve exists and has to be null, but that contradicts this assumption about conjugate points. Yes, so it gives you the sort of type of Shapiro effect which has to terminate. right? It is, as I understand it, is so what you do technically is you solve the Hamilton-Jacobi equation for the null geodesics. Okay, so that's it really. There are two approaches to mass I've discussed. There's quasi-local one based on isometric embeddings in R3 or H3, but maybe there'll be, starting for H3, maybe there'll be a way of relating it to this Wang Yao mass where you should really be embedding in R31. And the interest, as I see it here, is to extend these formulations to cosmological setups where it's less clear what reference space you should take. And then Penrose is one global based on causality and properties of space-time near I0. And they both, applicable to Kerr. So in the first approach, we've shown how to calculate the mass of all possible cross sections of Kerr horizons, including those with negative Gaussian curvature. And well, the second one, well, I guess the contribution here was to show that Kerr space-time, not only Schwarzschild, but also Kerr satisfies this Penrose property. So that's where I stop. Well, I mean, the extreme black hole where the mass is what it is, I mean, it's purely classical, right? But the extreme black holes, they're not supposed to be evaporating. So why would that? Well, there is this, well, not really, but there is this third black hole, third law argument, which tell you that the extreme black hole are precisely not the endpoints of a black, but they cannot be created in classical process.
But for non-experts, can someone define an extreme black hole?
The extreme black hole is well, so there is something called surface gravity, and because you have a stationary killing vector, so you can compute the surface gravity with respect to this killing vector, and that has to be 0 for extreme black hole. So there, this surface gravity is related to, is proportional to Hawking temperature, so they would have 0 Hawking temperature. But in the case of Kerr, so Kerr has two parameters. There is the mass and the spin, so M and A. And in order to avoid this naked singularities, the A can only have a certain range, so it cannot exceed M. And the extreme case is where A equals M. So is the, for a given M, for a given ADM mass, it's the fastest spinning black hole. Well, so this graph suggests that if you were to start with some fixed mass, but you would allow yourself to vary A, which means varying J. So by decreasing A, you're allowing yourself to increase the quasi-local mass. So there is an open set near the extremality value in the space of parameters where the mass is increasing away from the extremal black hole. I mean, all we can say with some confidence is that this is not a numerical artifact, but I have no intuition what, if any, is the physical interpretation of this.
In this extreme case, does it depend on I mean, can you do the same for extreme rational motion?
Yes, I'm just trying to think whether you can definitely find well you can do it for, I mean, for Rice and Nordstrom it's more easy. You can do it for Kerr, you can do it for Kerr Newman. You can do it for Kerr, which is better, but we haven't, that's not something we have done. So I do, you know, I know what the embedding is like, but I don't know what the integral of the mean curvature is like.
No, because I believe there is this work that apparently the third law of thermodynamics for the Einstein-Maxwell system is false or something like there is initial data that gives you an extreme Rice and Nordstrom.
So this is this recent work
Yeah.
by Unger and
Yeah.
So I've looked at that, but it's I think the verdict is open, from what I understand. Yeah.
No, I may look carefully.
So, of course, when people do stuff in higher dimensions, they're not really thinking of being asymptotically D. So you were just assuming you're on you can think of
Yeah, so it's called it's a name for it. It's called black string, right? Is that right? So if you take Schwarzschild cross, if you take a product metric, which is what you might be thinking of, a product metric of Schwarzschild and S1. No, it's in the thesis which you have examined. That's all I can say. In the St. Peter's thesis. So it yeah. So why isn't it here? So once your students stop being your students, they don't come to your talks anymore. That's what I've observed. So yeah, so my recollection is that it does.
So it
But,
does.
yeah. Well, you see, you're even for Schwarzschild with zero mass. So for zero mass, you cannot, you cannot. I'm going to pick a point on square minus and square plus, which has some v and u, and they may be both equal to 0. And on one, I pick pi equals 0. On the other one, pi equals 5. So if I started moving to the sort of to the left towards black hole on square minus, and to the left square plus, and I would start to construct this causal curve. The fastest causal curve would be this. So you can connect these 2 points by now. But by now line. But this is not, but in Penrose's property, you would want this to be a causal curve. So it doesn't satisfy Penrose's property, but for mass equal to 0, this fastest causal curve would be the one connecting multiple points on square minus and square plus. And then if you make the mass negative, you start with pi equals 0. You cannot even get to pi equals 5. You sort of stop before that. There is a formula depending on the mass, how close to pi can you get.
Questions we can answer again.